Welcome to the deep dive. This is where we, sift through the latest research, pull out the key insights, hopefully just for you. Today, we're diving into something pretty cool, actually. It's one of the most intriguing hunts happening in astrophysics right now, the search for these cosmic giants we can't even see. Stuff like black holes, neutron stars. And the way scientists are doing this, well, it involves something called ellipsoidal variables. Sounds technical, but we'll break it down.
That's right. And for this deep dive, we've really gone into some recent papers. There's a key one by Perryman and quite a few others looking at the just amazing data coming out of the Gaia mission.
Right. So our mission today really is to pull out the most important bits, help you get your head around what these unique objects actually are. And we'll look at how scientists are using them to try and uncover these hidden partners out there in space, even when they're totally invisible. Expect definitely some surprising facts, maybe a few aha moments along the way. Okay, so let's kick things off. Let's unpack this term, ellipsoidal variables. What exactly are we talking about here? My understanding is they're basically close binary systems, like two things orbiting each other really closely. Could be two stars, maybe a star and a planet, and their gravity is so strong it messes with their shapes.
Exactly, yeah. That's the core idea.
Yeah.
Because they're so close that neutral gravity pulls on them and they get distorted. They're not perfect spheres anymore. Think of them as being stretched out a bit, kind of egg-shaped or, well, ellipsoidal.
Hence the name.
Right. And as these distorted objects orbit each other, the amount of their surface that we can see from Earth changes slightly. So this causes a very regular but subtle pattern of brightening and dimming in their light curve. It's quasi-sinusoidal, like a smooth wave.
Okay, subtle brightening and dimming, but they don't block each other out. That's different from eclipsing binaries, right?
Precisely. That's a key distinction. Their orbital tilt. The inclination, it isn't edge-on enough for one to pass in front of the other from our perspective. No eclipses. Just this gentle wobble in brightness from the changing shape.
Got it. So beyond that main brightness change, are there other, even fainter signals hidden in the light, other clues?
Oh, yes, absolutely. There are other subtle photometric signatures we can sometimes pick up. For instance, you might see a bit of reflection, light from one star bouncing off the surface of the other, like a faint echo of light. And there's also something called relativistic Doppler beaming. It's a bit more exotic. Basically, because these stars are moving so fast in their orbits, Einstein's relativity comes into play. The star appears slightly brighter when it's moving towards us and slightly dimmer when moving away.
Wow, okay. So that's down to the speed itself affecting the light we see.
Exactly. It's a tiny effect, but with modern instruments, measurable. Fagler and Mazza pointed this out back in 2011.
So we're talking really tiny changes here. How small are we talking? What's the scale of this main ellipsoidal effect?
It's really small, even for the systems that are super close, say, separated by less than about 15 times the sun's radius. The change in brightness, the semi-amplitude, it's typically only a few percent.
A few percent, that's it.
Yeah, Morris and Naftalin established that back in '93. It's like trying to spot a tiny flicker. It requires incredibly precise measurements.
I can imagine. So how long have astronomers known about these? It sounds like something that would have been almost impossible to detect reliably, say, 50 years ago.
You're absolutely right. It was tough. Back in 1985, Morris listed only about 20 confirmed cases. Just 20.
Wow.
But then came the space-based telescopes, specifically designed for photometry, like Kepler, and more recently, TESS. They just stare at stars looking for these tiny dips and wobbles, and the numbers have just, exploded. TESS, the latest mission, has already flagged something like 15,000 candidates.
15,000, that's just staggering. From 20 to 15,000.
It really is a revolution in detection capability.
And it gets even wilder, right? Because you mentioned it's not just star-star systems. This ellipsoidal effect, it's also been seen where a planet is distorting its host star.
Yes, exactly. That's another fascinating angle. In some systems with massive planets orbiting very close hot Jupiters, the planet's gravity is actually strong enough to tidally distort the star itself. So the star bulges slightly toward the planet. And as the planet orbits, the star's brightness changes in that same periodic way.
So the star itself becomes an ellipsoidal variable because of its planet?
Precisely. We've seen this with planets like HATP 7b, that was one of the first, found by Barucki and the Kepler team in 2009. Also Corot 3, WRSP. Several confirmed cases now.
That's pretty mind-bending. Okay, so clearly astronomers are finding tons of these things now. But why all the fuss? Why are they so captivated by these Seemingly quite subtle changes in starlight. This is where it gets really interesting, isn't it? What's the big payoff?
Yeah, there are really two main motivations driving all this interest. They're quite different, but both really important. First, it's fundamental to understanding how stars, especially binary stars, evolve over time. These short-period binary systems are the starting point for some really dramatic cosmic events down the line. Things like cataclysmic variables, certain types of supernovae, and even the mergers of neutron stars and black holes that create gravitational waves, the kind LIGO and Virgo detect. Many of those probably started out as close binaries.
Ah, so studying these seemingly quiet systems now helps us understand those huge explosions and mergers later.
Exactly. By studying large, uniform samples of these ellipsoidal variables, especially from surveys like Gaia and 10S, we can test and refine our models of binary evolution. There are still lots of poorly understood processes in how close binaries interact and evolve.
Okay, so that's one big reason. Understanding stellar evolution and cosmic fireworks. What's the second motivation? You mentioned it was maybe even more exciting for some.
Right. The second reason, and this is really driving a lot of the current excitement, is their role in the hunt for unseen compact companions.
The invisible giants.
Precisely. We're talking about potential black holes, neutron stars, maybe even white dwarfs that are orbiting a normal star but are just too faint or maybe truly dark to be seen directly.
So it's like cosmic detective work. You can't see the culprit, but you see their effect on the partner.
That's a great way to put it. The idea itself isn't brand new. Way back in 1969, Trimble and Thorne were looking at a bright binary, HR 8427, and they speculated its unseen companion might be a black hole. They calculated a minimum mass for it of over 5 solar masses, which was suspicious.
But did it turn out to be one?
Well, no. That specific case got ruled out later. Morris and Naftalin, in that 1993 paper we mentioned, used the ellipsoidal light variations of the visible star. Their analysis showed the companion mass was likely much lower, effectively ruling out the black hole hypothesis for that particular system. But it showed the potential of the technique.
Okay, so how does that work in principle? How do you go from a slight dimming to suspecting a black hole?
The core idea is this. If you can measure that ellipsoidal amplitude, the amount of brightening and dimming, if you know the mass and radius of the visible primary star,
Right.
then you can actually calculate a minimum possible mass for the unseen companion needed to cause that distortion.
Okay, a minimum mass. And if that minimum mass comes out really large.
Exactly. If that minimum mass is significantly larger than 1, meaning the unseen companion must be at least as massive or likely much more massive than the visible star, well, that flags the system. It becomes a really interesting candidate for potentially hosting one of these dormant compact objects at a neutron star or a black hole.
Because a normal faint star wouldn't usually be that massive compared to the bright primary, right?
Generally, yes. So a high minimum mass ratio is a strong hint something unusual is going on.
But you said there was a big if. The primary star's mass and radius. How often do we actually know those well?
That's the major hurdle. In most cases, especially for stars discovered in large surveys, we don't know the primary star's mass and radius accurately enough. They're really hard to pin down without detailed follow-up.
So that sounds like a pretty big roadblock. How do scientists actually get around that? How do they make progress if they're missing that key piece of information?
Right, that's been the challenge. How do you sift through thousands of candidates without knowing those crucial parameters? And this is really where the European Space Agency's Gaia mission has been an absolute game changer.
Gaia. We hear so much about it. It's mapping the galaxy with incredible precision, right?
Incredible is an understatement. Gaia is providing this just unprecedented hunting ground for all kinds of binary systems. For instance, for binaries that are far enough apart that Gaia can actually see both stars, El Badri and colleagues used Gaia data in 2021 to identify something like 1.1 million resolved systems.
1.1 million. Wow.
And that's just the wide ones. For the closer systems, the ones relevant here at Gaia Data Release 3, or DR3, it includes orbital solutions for about 800,000 binaries, found through different techniques, astrometry, spectroscopy, eclipses.
So it's finding binaries left, right, and center. And what about specifically for these ellipsoidal variables we're talking about?
Well, the numbers there are huge, too. In 2022, Rimaldini and collaborators combed through Gaia DR3 light curves and identified over 65,000 candidate ellipsoidal variables.
65,000 potential systems.
Yeah. Now, you have to be a bit careful the researchers acknowledge that. The automated processing means some of those might be, contaminated. Maybe there are actually other types of variables like WUMA eclipsing binaries that can sometimes look similar. But still, The sheer number is astounding.
Okay, but we still have that problem of not knowing the primary star's mass and radius for most of them. How did Gaia help with that, or was there another trick?
There's a very clever trick. This was proposed by Gomel and colleagues in 2021. They tackled that unknown mass radius problem head on. Instead of needing the actual mass and radius, they introduced something called a modified minimum mass ratio. Let's call it MMM.
Modified minimum mass ratio.
Okay.
How does that work?
It's based on a neat assumption. They basically asked,
Right.
what's the maximum size the primary star could possibly be in that binary system before spilling material onto its companion? That boundary is called the Roche lobe.
Ah, the Roche lobe, the gravitational point of no return, sort of.
Kind of, yeah. So they assumed, for the calculation, that the primary star fills this Roche lobe. It's as big as it can possibly be. By using that assumed size in the ellipsoidal variation equations, they could still estimate a minimum mass for the unseen companion.
But based on an assumption, how reliable is that?
Well, here's the crucial part. This modified minimum mass ratio, the MMR, is always smaller than the true minimum mass ratio, which in turn is smaller than the actual mass ratio.
Okay, so it's like a lower floor on the estimate.
Exactly. It's a conservative lower limit. So the logic goes, if even this conservative MMR value comes out greater than 1, then the actual mass ratio is very likely significantly greater than 1.
Meaning the unseen companion is almost certainly much more massive than the visible star.
Precisely. So any binary system where the MMR is calculated to be greater than 1 becomes a really strong candidate for having a massive, unseen, compact object secondary. It's a powerful filtering technique.
That is seriously clever. So did they apply this MMR method to the Gaia data? What did they find?
They did. Gomel and his team applied it to the Gaia DR3 candidates in a 2022 paper. And the results were, well, pretty exciting. They found over 6,300 short-period ellipsoidal candidates that showed a decent brightness variation and had an MMR greater than 0.5. That already suggests a potentially massive unseen companion.
6,000. Okay.
But even more compellingly, they found 262 systems where the MMR was greater than 1.
Over 250 systems flagged as having a very high probability of a massive unseen companion.
Yeah, especially if the visible primary star is a normal main sequence star. For those systems, it significantly boosts the odds that the companion is indeed a neutron star or a black hole.
That's a fantastic haul of candidates, but I sense there must be some caveats, right? Assumptions made.
Absolutely. And the researchers were very clear about this. The whole method hinges on two key assumptions. First, that the light variation they're seeing is purely due to the ellipsoidal effect and not contaminated by other things like star spots or pulsations.
Well.
And second, that the primary star is what they assume it is, usually, a main sequence star filling its Roche lobe for the MMR calculation. If the star is actually something else, like a giant star, the interpretation changes.
So what does that mean practically?
It means follow-up observations are absolutely crucial. You can't just take the MMR value as proof. You need to go back with telescopes, get spectra, measure the radial velocity of the visible star properly. That's the only way to confirm the mass estimate and really verify these candidates.
Right, the detailed groundwork still needs to be done. Were other groups also mining Gaia DR3 for these things using similar ideas?
Yes, definitely. Gaia DR3 really opened the floodgates. For example, Fu and colleagues, also in 2022, did a search and initially found 10 interesting targets. After carefully ruling some out, they were left with 2 strong candidates for hosting compact objects.
2 strong ones there. Any others?
And then Shahaf and her team in 2023 identified 177 systems where they believed there was a probable non-luminous massive companion based on Gaia data. Among those, they highlighted 8 specific systems as candidate black hole binaries, where the inferred mass of the compact object was larger than 2.4 times the mass of the Sun.
8 potential black hole systems from that search. That's significant. Did the Shahaf study find anything else interesting about the larger group of 177 candidates?
They did, actually, something quite fascinating. When they looked at the properties of the other 169 systems, the ones not flagged as black holes, they saw clear separation. There seemed to be 2 distinct populations based on orbital eccentricity and mass.
Oh, what were they?
One group looked like white dwarf binaries. They tended to have low eccentricities, nearly circular orbits around 0.1, and the unseen companion masses clustered around 0.6 solar masses, typical for white dwarfs.
Okay, so a white dwarf group.
And the other group looked more like neutron star binaries. These had noticeably higher eccentricities, typically around 0.4, and companion masses clustering around 1.3 solar masses, which is bang on for neutron stars.
Wow. So the orbital properties alone were hinting at whether the unseen companion was a white dwarf or a neutron star.
It appears so, statistically at least. This is a pretty neat result,
Mm-hmm.
suggesting we might be able to start classifying these unseen objects even without direct detection, just based on how they affect their partner's orbit and the system's overall properties.
Okay, so Gaia is clearly, completely changing the game here. It's providing this huge uniform survey, finding candidates by the thousands, and these clever techniques like MMR are helping to filter them.
Ah,
And future Gaia data releases are expected to give even better light curves, maybe even astrometric orbits for some of these. The potential seems enormous.
it really does. The sheer volume and precision are unprecedented. However, and this is where the story takes an interesting, perhaps slightly unexpected turn. The initial excitement from finding all these candidates has been, let's say, tempered a bit by some of the first follow-up observation campaigns.
So the crucial verification step you mentioned, what happens when scientists actually point telescopes at these specific candidates to get those detailed measurements?
Well, some of the initial results have led to what's been described as a disappointing yield, at least in terms of finding confirmed black holes or neutron stars straight away.
Disappointing yield. How so?
Okay, so take the work by Nagarajan and colleagues in 2023. They specifically selected 14 of those promising candidates identified by Gomel's team, the ones with high MMMR values, and they performed detailed spectroscopic follow-up.
Right, the essential next step. What did they find for those 14?
Well, the results were quite revealing. They measured the radial velocity curves for the visible stars very precisely. From that, they could derive much more reliable minimum masses for the companions, and in all 14 cases, the minimum companion mass came out to be a zero point 0.5 solar masses or less.
Zero point 0.5. That's much lower than expected for a neutron star or black hole, right?
Much lower. And if you assume the orbits have random inclinations, which is standard, the typical companion mass was even smaller, estimated around only 0.15 solar masses.
So tiny compared to the visible star, likely. Definitely not black holes or neutron stars in that bout.
Exactly. It made it highly unlikely that any of those particular 14 candidates, despite looking promising based on the initial Gaia light curve analysis and the MMMR, actually contained a heavy compact object.
Hmm. So if it's not a black hole or neutron star causing that ellipsoidal-like signal, what is going on in those systems? What could mimic that effect?
That's the million-dollar question they tackled. Nagarajan and her team proposed several alternative explanations based on their detailed modeling. They found that the observed light curves and their new radial velocity data could often be well explained by other scenarios,
Such as?
such as models involving unequal mass contact binaries, where the two stars are actually touching but with significant star spots on their surfaces. Star spots can cause brightness variations that might contaminate or mimic the ellipsoidal signal.
Okay, star spots messing things up. What else?
Or perhaps they were looking at detached main sequence binaries, just normal stars orbiting each other, where maybe the light curve analysis wasn't quite capturing the whole picture. And in some cases, it might even be single stars. Certain types of pulsating stars or stars with very large spots rotating in and out of view could potentially create variability that, in a large survey like Gaia, gets mistakenly classified as ellipsoidal.
So the universe has other ways of creating these subtle wobbles in starlight. It's not always a hidden giant.
It seems so. It highlights the challenge and the importance of that careful follow-up work. The initial filtering with methods like MMMR is powerful for finding candidates, but confirming them is another story.
Right. So despite these, let's call them initial setbacks or maybe refinements on specific candidates, the overall feeling isn't that the method is flawed, just that it needs careful application and verification. The hunt still goes on.
Oh, absolutely. The outlook remains positive overall.
So wrapping this up then, what does this all really mean for the big hunt, the search for these quiescent, hidden black hole companions? It feels like the universe is throwing us some curveballs, giving us subtle clues that maybe don't always mean what we first think they mean.
That's a good way to put it. Yes, the universe is subtle, and interpreting these signals is complex. While these first few spectroscopic follow-ups on some of the Gaia candidates haven't immediately uncovered that, definitive black hole goldmine everyone was hoping for, the methods themselves are constantly being refined, and the sheer volume of data still coming from Gaia, plus other missions like TESS, means the potential for discovery is still absolutely immense. We're learning more about how to interpret those light curve wobbles correctly, filtering out the imposters.
So the hunt very much continues, maybe with slightly adjusted expectations, but still with powerful tools.
Exactly. We're getting better reading the signs.
Which leads to a final thought, maybe for you listening. As our instruments keep getting sharper, our models more sophisticated. Just how much more are we going to be able to figure out about the hidden universe without ever actually seeing these objects directly? What other invisible cosmic partners might be out there waiting to be found just by patiently watching the subtle dance of the stars we can see?